It was brought to my attention that the Coset video didn't get uploaded, and then I purged my videos folder. So let's just quickly go through that, and I'll put this in the right spot. So if we have a ring and an ideal in that ring, then a coset of I is a subset of the form A plus every element of I. So you take all of the elements of I and you add them to this fixed guy A. So A here is fixed, and we sum A with all the elements of I. Now this is a set, right? We have these braces here. So it's a set and it's a subset of R. Okay? And it's called a coset or a left coset. And this is what it is. And the collection of all of these cosets is denoted by R mod I down here. R mod I is just throw all of those cosets into the same set. We'll also write R bar if I is understood, bar from the from back in integer land. Okay? So as just an example, let's work out some cosets. Suppose R is Z and I is the collection of all multiples of 3. Then 0 plus 3 is a coset because it's an integer plus the ideal. And it's the collection of all 0 plus k's, where k is an element of 3. Now we can actually, of the ideal generated by 3, we can actually write out what k looks like. It has to be a multiple of 3. So this is just the multiples of 3 themselves, and we get 3. One way to interpret this is we take the element 0 and we throw it into the ideal using plus. But this is an ideal. It already has 0. So throwing it in doesn't do anything. So 0 plus 3 remains 3. We can look at the next couple of cosets. So if we look at 1 plus the multiples of 3, we get 1 plus the multiples of 3, and that's really it. Again, this is a very large set. If we were to sit here and we were to write out elements, we'd get like, 1, 4, 7, and so on. And we would get like -2, -5, and so on. And similarly, if we do 2 plus the multiples of 3, this is a very large set. We get like 2, 5, 8, and so on. And -1, -4, -7, and so on. So these sets are quite big. But this is just what they are. So we have these 3 cosets here. Let's go on to the next one. 3 plus the multiples of 3 looks like 3 plus the multiples of 3, but we can factor out a 3 from this. So we get 3 times 1 plus m, but m ranges over all integers. So as m ranges over all integers, so does 1 plus m. So we do this sort of substitution here. N is 1 plus m. So we again get all of the multiples of 3, which is the same as this, which is the same as 0 plus 3 from before. This should remind you of z mod 3. Right? We're sort of wrapping back around once we hit 3. We're wrapping back around to 0. Similarly, we can do the same thing with 4. 4 plus the multiples of 3 is 4 plus the multiples of 3. 4 we can write as 1 plus 3. And then we can sort of absorb this 3 into the multiples of 3. And we get this expression. So 4, the coset that is represented by 4, is the same as the coset that's represented by 1. Similarly, the coset that's represented by 5 is the same as the coset that's represented by 2. Great. And just to see this again a little bit differently, 34 we can write as, well, 1, sorry, it's going up and down. 34 we can write as 3 11s plus 1. Those 3 11s we can absorb into the multiples of 3, and we get 1 plus the multiples of 3. So this should remind you pretty seriously of modular arithmetic, and this is the natural generalization to an arbitrary ring of modular arithmetic. Instead of having a single guy, that single guy in this case principally generates an ideal, and we're looking at congruence modulo that ideal. But this is an example of something called coset arithmetic, which we will get a lot of practice doing.